Hello everyone, my name is Eduardo Costa. I'm a research associate at the University of Bath, and I'll be presenting some of the work that we've been developing on digital design of non-prismatic reinforced concrete beams in the scope of a research project called Automating Concrete Construction. In the context of the present climate emergency, the construction industry needs to change. In the United Kingdom, for example, the construction industry is responsible for nearly half of the country's carbon emissions, in part due to the use of an extremely large volume of concrete. It is the world's most widely used man-made material, accounting for more than 5% of global CO2 emissions. In order to improve the sustainability of the construction sector, the UK government has set 4 goals to be achieved by 2025, which include a 50% reduction in greenhouse gas emissions in the built environment. Following that lead, we are working on a research project titled Automating Concrete Construction, or ACORN for short, which aims at improving whole life sustainability and productivity in the building industry by defining a holistic approach to the manufacture, assembly, reuse, and deconstruction of concrete buildings. One objective is to reduce the material of concrete structures with an embedded consideration of automation of construction. This research project represents a transitional pathway for low-carbon concrete design, paving the way towards carbon neutrality. Today we present some early results from the project. In its quest to ensure that just enough material is used and no more, we are investigating ways of optimizing beams and slabs for off-site mass customization, towards reducing their embodied carbon, with a particular focus in the use of flexible formwork for concrete manufacturing. In particular, we present the development of a computational design tool with the intent of catalyzing the adoption of such an approach by the construction industry. Our approach to reduce material and subsequently the embodied carbon of concrete structures is through promoting the use of non-prismatic concrete elements. Traditional methods for producing concrete elements use orthogonal rigid panel formwork, resulting in prismatic building elements. Such is not because it is difficult to shape concrete to other forms since it begins life as a liquid, or because an element needs to be prismatic to support its load, but because a prismatic formwork is easier to build. It has been shown that up to 50% of the concrete in a typical beam is only there because of the prismatic formwork it was made in, and could be removed. For too long, the industry has used ease of construction as an excuse to waste material. Therefore, we are implementing a computational design tool to generate optimal forms for non-prismatic reinforced concrete elements that takes into account the constraints imposed by the fabrication process. The design of non-prismatic concrete elements will be governed by a design system that articulates 3 modules, namely generation, analysis, and optimization, and is informed by manufacturing constraints. This work precedes the fabrication of 1-to-1 scale physical test specimens. Presently, the adopted optimization approach looks for designs that, while their performance satisfies their design requirements, use just enough material and no more. In case of beams, an element's performance is currently assessed in terms of serviceability, particularly in terms of deflection. The analyzed beam designs are provided by the generation module, which is developed towards flexibility by representing a wide spectrum of shapes and structural configurations. The paper focuses on the first 2 modules, generation and analysis, as applied to the design of non-prismatic beams. The generation module is responsible for creating the shape of a reinforced concrete element through a parametric modeling approach, which enables effective production of design alternatives adapted to boundary conditions. Presently, 2 templates are implemented, capable of generating T-shaped beams and fabric form beams, which are defined by NURBS surfaces as well as by additional corresponding information. T-shaped beams were selected as they are fairly common, typically studied in structural design textbooks. On the other hand, the choice for fabric form beams derives from existing expertise on the subject within the project's team. Note that standard rectangular beams can also be generated using the T-beam template. We'll use the T-shaped beams to illustrate our approach to the generation and representation of non-prismatic beams. Complying with the principle that every cross-section in a beam remains plane after deformation, the shape of a non-prismatic reinforced concrete beam is described in ACORN by a number of cross-sections. Given the required parameters associated to cross-sections, which can vary along its length, the corresponding T-shaped cross-sections are determined, which in turn are used to generate the beam's shape. Additional parameters pertain to the beam itself and remain constant, such as its span, material properties, and number, diameter, and type of reinforcement bars used. On the other hand, generating the shape of fabric-formed beam implies simulating the behavior of concrete poured inside fabric formwork, for which we opted for a numerical approach. An iterative method was used to form-find the section shape corresponding to a variation of the elastic curve, which takes into account the effects of both gravity and the hydrostatic pressure of the poured concrete. The form-finding procedure was extended to determine the shape of fabric formwork when restrained with internal ties, expanding the design space of the beam's shape. For preliminary validation, the algorithm was used to match the shape of a previously fabricated 60 cm long fabric-formed beam. The generated model was then compared with the mesh that resulted from 3D scanning the physical model of the existing beam. Looking now at the analysis module, its main purpose is to determine the performance of a given beam design. Deflection was selected as a first indicator for performance, since in the case of buildings, serviceability is often the limiting factor over strength. In our analysis module, deflection is calculated numerically through the method of integration of curves. The main advantage of the implemented module over existing plug-in solutions is its capability to analyze non-prismatic geometry, as well as take reinforcement steel into account. The estimation procedure consists of the following. We begin by dividing a beam into a number of equally spaced planar sections. Since we are representing the shape of a non-prismatic beam by a set of cross-sections, those cross-sections will be used in the process. For each of those cross-sections, we generate a set of strain diagrams within an increasing range of strain values at the beam's topmost fiber between 0 and the ultimate strain for concrete. For each strain value and corresponding diagram, we determine the neutral axis iteratively by testing hypothetical strain diagrams and balancing compression and tension forces both in the concrete and reinforcement steel. After determining the neutral axis, we are able to calculate the resisting moment for that strain value, currently around the centroid of the tension rebar's cross-section. Now, for each of the beam's cross-sections, we are able to plot a graph of resisting moments against curvatures, which are calculated from the slope of the strain diagrams. Then we determine the curvature at the section point from bending moment. Finally, we integrate the beam's curvature over beam's length to determine the slope, and integrate slope over beam's length to determine deflection. Adding to calculating deflection, the tool provides information about strength by identifying failure at individual sections. The analysis module was validated by comparing its results with published experimental data consisting of a series of short-term load tests on reinforced concrete beams. Considering these as benchmark prismatic beams, one of them was replicated using the generation module and then run through the analysis module, generating the corresponding moment curvature and deflection plots. A load deflection plot was used to compare the results with the benchmark beams. Comparing both load deflection plots, we considered the analysis module as valid, particularly considering that the benchmark plot resulted from a physical test and the acorn plot results from a digitally simulated beam. In summary, by facilitating the design of non-prismatic reinforced concrete elements, the acorn design tool aims at rendering such approach available to current design practices, enabling structural designers to design more sustainable concrete elements with confidence, rigor, and speed, and therefore mitigating the obstacles that prevent them from using just enough material. Following the development of the generation and analysis modules, an exploration of the optimization module will begin by experimenting with existing plugins for Grasshopper. As the project advances beyond beams, non-prismatic concrete slabs are being addressed, particularly looking at thin shells due to their structural efficiency and reduced material. So thank you very much for listening, and I'm looking forward to your questions.